Let's find the interval of convergence for this power series. So we're going to do the ratio test. And so we're going to take the limit as n goes to infinity of, we don't need absolute values here because this isn't an alternating series. So we're just looking at the nth plus first term. So that's when we replace n with n plus 1. And in the denominator, be careful when we replace n with n plus 1, we have that coefficient there. So we have to remember that we're really distributing that guy. And then divided by the original term, which I'm going to just write as multiplying by the reciprocal of the original. Okay, so this is the ratio test. So again, it's the nth plus first term over the nth term. And some of you have been dividing backwards, so let's make sure we're really careful about that. Okay, and it does matter which way we go, because obviously if we get a value greater than 1 versus less than 1, it's going to matter which one's the numerator, which one's the denominator. Okay, anyway, so back to this. We're going to simplify, we're going to rewrite the numerator as 3x to the n times 3x to the 1. So of course the property that we're using here is that x to the m times x to the n is the same thing as x to the m plus n, right? So we're just going in the opposite order. We're given something with a sum, we just break it up, we're breaking it into its factors. And in the denominator we have 2n plus 2 factorial. And then the rest is as it's written. So we see here that as we're written, we can cancel a 3x to the n. But how do we deal with this 2n plus 2? So remember that 2n plus 2 is the same thing as, 2n plus 2 factorial is 2n plus 2 times 2n plus 1. And we keep going 1 less than the previous term until we get down to 1. But once we get to 2n factorial, we can stop because we want to cancel the 2n factorial with the 2n factorial. Okay, so all we're left with here is the limit as n goes to infinity of 3x is left in the numerator, and 2n plus 2 and 2n plus 1 is left in the denominator. So in terms of n, as n grows large, the numerator just stays 3x, but the denominator goes to infinity. So this whole thing goes to 0. Now by the ratio test, remember that the ratio test says that if the result is less than 1, it converges. If it's greater than 1, it diverges. And if it's equal to 1, it's inconclusive. So we have a result that's less than 1, and it's less than 1 regardless of the value of x. So this is less than 1, less than 1 always, regardless of x. So we're asked to find for what values of x does this power series converge, right? That's another way of asking what's the interval of convergence. So this converges for all values of x. So it converges for all values of x from negative infinity to positive infinity. So the interval of convergence is negative infinity to infinity. By the way, if we had asked, the radius of convergence, which is the distance from the center to the endpoint, is also infinity. Speaking of the center, note that the center of this power series is 0 because it's the value of x that if you replaced x with a 0, it makes the entire series 0. So the center is the value that if you replace x with that value, you get 0. Okay, so let's look at another example. Here's another power series. While we're talking about centers, this one is centered at 2. And one way you can see that is because if you substitute 2 in for x, you're going to get 2 minus 2 is 0, and the whole thing goes to the 0 series. The other way to think about it is that in general, the center is the value a that you're subtracting off. And this was to the nth power in general, but or it could be to the nth plus first. So, okay, so that's the center. So again, we're trying to find the interval of convergence. So let's do the ratio test. Get in the habit of writing what tests you are using. So we're taking the limit as n goes to infinity of the nth plus first term is going to be replacing all the n's with n plus 1. So this is going to be now to the n plus 2 power. And the denominators is going to be n plus 2, 3 to the n plus 2, and then flip and multiply by the original. Okay, now let's try to simplify this thing. So in the numerator, I'm going to write this as x minus 2 to the n, x minus 2 squared. And I'm going to leave this n plus 1. And then this I'm going to write as 3 to the n times 3 to the 1. Now in the denominator, I still have this n plus 2, but I can write the 3 to the n, 3 to the 2, and x minus 2 to the n, x minus 2 to the first. Okay, I cancel factors only, so I'm canceling the x minus 2 to the n, x minus 2 to the n, 3 to the n, 3 to the n. I can cancel one of the x minus 2's. Oh, sorry, wrong one. That's not x minus 2. Let me undo that. Or maybe I can just Control Z, Control Z, Control Z. There we go. We don't want to cancel that. Okay, right? This is x minus 2. This is x minus 1. Sorry. But I can cancel one of the 3's with that 3. Okay, so I can't cancel any of the x's here. I can't cancel any of the x's here. I can't cancel any of the n plus 2 with the n plus 1. So let's see what's left. In the numerator, I've got x minus 2 squared, and I've got an n plus 1. And in the denominator, I've got n plus 2, a 3, which I'll write out front just because it looks like a coefficient, and an x minus 1. And now I'm feeling like something went wrong. Oh, okay, sorry. Ugh, I hate making mistakes on videos especially. Okay, sorry. Down here, this x minus 2 to the n times x minus 1, this should have been a 2. Okay, so sorry for this confusion. That means that I could have canceled one of these things. Okay, sorry guys. Hopefully you're with me on this. Okay, so let's maybe double check what we just did. So the x minus 2 to the n plus 1 factors is x minus 2 to the n, x minus 2 to the 1. I can cancel one of them, and now I'm left with a single x minus 2, an n plus 1, a 3, and an n plus 2, but no other x's. Okay, so this is what's left. Now, as n grows large, the numerator has an n to the first degree, and the denominator has an n to the first degree. So the degree of the polynomials in the numerator and the denominator are the same. So that means that this limit is going to equal the ratio of the leading coefficient of the numerator over the leading coefficient of the denominator. So leading coefficient of the numerator, this whole thing, x minus 2, is the coefficient. So x minus 2, and then in the denominator, the coefficient is 3. Okay, so ratio test says that this thing converges for values where this is less than 1. And since we're talking about in terms of x, we really should keep this in absolute values because x could be positive or negative. So I'm going to put the absolute value of this thing is less than 1. Okay, so for what values does that equal? So that's the same thing as for what values x minus 2 over 3 is between negative 1 and 1. Okay, algebraically now I have to solve this inequality for x. So what can I do to isolate x? Well, the first thing I want to do is I want to get rid of this divided by 3. So I'm going to multiply the entire inequality by 3. So that's going to give me negative 3 is less than x minus 2 is less than positive 3. Now again, still trying to get x by itself, so I'm going to add 2, but I have to add 2 to all 3 parts. So I get negative 1 is less than x, which is less than 5. Okay, let's take note that my center is 2. Is 2 really in the center between negative 1, 0, 1, 2, 3, 4, 5? So here's my center. Is that really the center between negative 1 and 5? And it is. So here visually we can see that our radius of convergence is 3 because it's the distance from 2 to either one of our endpoints. Okay. Now our interval of convergence is going to be between negative 1 and 5, but we haven't yet checked what's happening at negative 1 and what's happening at 5. So the reason we have to check the endpoints is, remember, the ratio test tells us this thing converges for values when values of x that make this thing less than 1. But it also tells us that the ratio test tells us that it's inconclusive when the absolute value of x minus 2 of 3 is equal to 1. Those are, of course, by the same algebra over here, going to be the values. Well, let me do it. So this is the same thing as x minus 2 equals 3 is equal to plus or minus 1. So that's when x minus 2 is equal to plus or minus 3. And then by adding 2 to both values, x is either going to be a negative 3 plus 2, which is negative 1, or a positive 3 plus 2, which is 5. So these two endpoints we have to check separately. Okay, and that's always going to be the case. That's going to be the endpoints where it's inconclusive. So I'm going to go ahead and erase this because we need this space. So what we need to do is we need to check to see what's happening when x is negative 1 and what's happening when x is 5. So let's let x equal -1. And remember that what I'm doing is I'm replacing x in my power series with -1. So -1 minus 2 is -3 to the n plus 1 over I have my n plus 1 and 3 to the n plus 1. So I have a -3 to the n plus 1 and a +3 to the n plus 1 over here. So let's be careful here and realize that that's the same thing as -3 over 3 all to the n plus 1. And then I still have this over n plus 1. So why am I doing this algebra here? I'm trying to combine these because I'm trying to see what kind of series this really is. Okay, so if I do this little bit of algebra, I realize that in fact, this is just the alternating series -1 to the n plus 1 over n plus 1. And now it becomes a much easier series to try to evaluate if it converges or diverges. Now, does this mean that if you didn't recognize that and you did the some test on this, you wouldn't be able to figure it out? No, not necessarily. It's just that this is going to be a much easier series to try to deal with. Okay, so this is an alternating series with a sub n being 1 over n plus 1. So we can see that 1 over n plus 1 is going to be greater than 1 over n plus 2. So it satisfies that part of the test. And then the second part is that the limit as n goes to infinity of 1 over n plus 1, that's going to 0. So that also works. So the series converges when x is equal to -1. So we are going to include -1 in our interval of convergence. Now we have to check what's happening when x is equal to 5. So let's let x equal 5. And again, we're plugging x back into the original power series. So it's going to be 5 minus 2, or 3 to the n plus 1. And then we still have a over n plus 1, 3 to the n plus 1. Okay, in this case, the 3 to the n plus 1 over 3 to the n plus 1, that all cancels. So this is really just the same thing as the series 1 over n plus 1. Now, this isn't the harmonic p-series, but it behaves very similar to the harmonic p-series. So we can compare to our, oops, that is a bad sigma. We can compare to our divergent p-series. Now, unfortunately, we are adding in the denominator, which makes these terms smaller. So we can't do direct comparison with this, but we can do a limit comparison. To limit comparison, we take our original and divide it by the one we're comparing it to. So this is going to turn out to be n over n plus 1, which gives us 1. So this is some limit that is greater than 0. So the limit comparison test tells us that they both must behave the same way. So this one also diverges. This diverges 2. So that means when x equals 5, we get a divergent series. So we do not include 5 in the interval of convergence. So our interval of convergence is including -1, but not including 5.